In the next project, why don't we build a 2D simulator to model an outbreak? So this is inspired by a recent article from the Washington Post, where they have these graphical visualizations of what we can call cells moving around in a 2D space, sort of at random, and colliding or intersecting with one another and becoming infected, and then over time becoming immune or healed from the infection. And this was an article that was really fantastic. I'll link to in the comments on why outbreaks can spread exponentially and how staying in place and other mechanisms can reduce the spread. So to get started with this project, we're going to be pulling in some helper code. And this helper code is going to be linked to in the comments. And there are 4 files we're going to set up to get going on this next project. All right. So I'm going to set up a directory in my projects directory named PJ02. And I'll walk through just a quick overview of these 4 files that we'll be using. So the first file is a special one named __main.py. And this probably looks kind of familiar. When you've seen the __main, you know that that has to do with starting and running a program. And that's what this file is going to be about. So I'm going to copy in the main.py contents and save it. And you'll notice there are going to be some errors because this file is importing from a couple of other places. So I'm going to go ahead and set up a new file. And the next file is going to be model.py. And we're going to have a few classes in our model. So I'm going to copy in all of this code from my model that includes the class point, the class cell, and the class model. We'll come back and talk about what all of these things are in just a moment. The next file we'll import are some constants. And so I'm going to set up a new file named constants.py and drop in some named constants that this simulation will be using. We'll come back to. And then lastly, we're going to have a really funnily named file named view controller. And a view controller is a concept that you'll learn about in upper division computer science course on software architecture. And it's going to be the file that has the most support code that you're going to be able to ignore. But effectively what the view controller is going to do is be responsible for drawing and updating the screen. All right. So now that we've in running the model such that over time it updates itself. Okay. So that's a lot of support code to pull in. I would encourage you to pause the video and get these 4 files set up. And once you do, to test what's going on, you can run python-m and then projects.pj02. And this will be this is kind of a different way of running a project than we've seen before, right? We're saying just the name projects and PJ02, and notice that we're not using __main. When we have a file with this special name or a module with this special name in a directory or a package, it makes that entire package runnable as if it were its own module. And so here we can just run this, and what you should see if this works is an empty canvas, right? And we're going to be working on filling out this canvas in the next couple of videos. Great. So what's all this support code? First, the main function is found in main.py. And you'll notice that what it's doing is setting up a model, which we'll go and look at. But this is going to be the model of our simulation. And it's going to have, the model should be setting up some number of cells and the speed at which they're going to be moving as the initial parameters. And then it's going to have a view controller, right? And so the view controller is going to be given a reference to the model, and it's going to be updating the model or saying, hey, model, move on to the next time tick. And it'll automatically render or visualize the state of the model once we've updated it. Constants, as I mentioned, are having to do with things like the size of our area that we're working with, and then the radius of our cells that will be the circles on our screen, things like that. And our default speed, our default cell count is going to be 1. View controller, I'm not actually going to spend any time on. We'll come back to it once we've got a little bit more familiarity with the model. So the model is where you'll be spending most of your time. And you'll notice that we are, as we looked at in the previous video, importing from future Python the ability to annotate, use a type a class name inside of the class definition. So with our class point, we've got an add method that can refer to the class point from within it. And that's why we needed to include that. And remember that this line must be the very first line of a module if you make use of it. So your author field that I would encourage you to go ahead and fill in will be down here. All right, we'll make use of some of these other imports as we move through this quick tutorial. So we've got a point that's going to represent a 2D Cartesian coordinate point that has a constructor. That's all great. And then we have the idea of a cell. And a cell is going to be made up of a few attributes for the time being. The first is its location, which is going to be a point. This will be where this cell is located in our 2D coordinate plane. The next is going to be a direction, which it feels a little bit funny to think of a direction as a point. But the intuition here is that if we move the point by saying, okay, we've got some point here and let's say it's moving in this direction, right? And let's say this direction, let's say this is 0, 0, and it's going to, in the next time step, move to 1, 1. You could say that its offset is going to be what we think of as a vector of with coordinates 1, 1. So we can represent this arrow, right, from the origin as just a point. And then if we want to move a cell, no matter where it is, we can add one cell's location with the direction it's moving in based on that point add method, right? So if we go look at that again, we see that just adds these two things together. And that will give us back a new point that would be like the new location of a point, right? So this will be something that we do in just a moment. And we're going to have some other methods like what color to model a point as in our visualization, things like that. Next, the model itself is going to keep track of our population, which is a list of cells, right? So we need to initialize a population. It's going to keep track of how much time has passed, and we might use that as part of our project to potentially chart out how the simulation evolves over time. And it's got a constructor that we actually still have more work to do. Notice the constructor of a model should be setting up some number of points and using speed in some way to set their how fast they're moving or the directions, the velocity of the directions they're moving in. And so this population is currently empty. We have some more work to do here. But before we get into that, just a few more things. The tick method, you're going to hear the word tick quite frequently when you're thinking about graphics in a simulation or if you're making a game. And the idea is like a clock, like each tick, we need to update the state of our model to move all of our cells around and carry out some other logic. We're going to make use of, we want our cells to begin in random locations and random directions. We're going to come back to these two methods, helper methods, in just a moment. And ultimately, we want to make sure that our cells stay in bounds. You'll notice that in the Washington Post simulation, our cells bounced off of the various walls. And those walls will be, or the bounds of our simulation are driven by these variables in constants.py. Part of the project that we're not going to get to today is determining when a simulation is complete. And for example, in the Washington Post article, once every cell has become either sick, recovered, or once there are no more cells that are sick, that means there's no more contagion that can spread, the simulation would be complete. But we're not going to worry about that method for now. All right, so this is a starting point, and now the question is, can we go ahead and initialize our population? So we've got this parameter named cells, and we've got a population that's an empty list of cells. So let's go ahead and say for n in cells, right? Or we could say for I in cells if we wanted to. So we want to run a loop. We want a loop. And actually this is an integer, so we need to set up a range, right? We need I to be within a range of 0 to however many cells we want. And now what we want to do is construct a brand new cell, right? So how do we do that? Well, we know in our cell class, we've got a constructor that says you have to give it a point and a direction. So for now, let's just set up in the constructor of this particular of the model, we're going to set up a starting direction, starting dir, and that will be the result of calling, let's say, random starting location, starting loc or location will be random location. And I'm trying to call this method, right? It's my helper method named random location. We need to go implement random location, right? We haven't done that yet. So I'm going to say self.random location. Remember, a key difference between a function and a method is how we call it. And in order to call a method, we have to call it on some object. And the object that we're going to call this method on is myself, right? I'm trying to initialize myself. So I'm saying, okay, this model object that's being initialized, I want you to call this helper method named random location to produce a random location. Notice that this random location is currently just 0, 0. We've got more work to do there, but this will at least start to hook up the logic of our initialization. Next, we'll do a starting direction. And remember, this is the direction a cell is going to be moving in. So self.random direction is another function or method, I should say, we'll go implement. And you'll notice that in thinking ahead to where we're going, we want to provide an argument to this method that's the speed or some magnitude that we can use to make our cells move faster or slower if we wanted to play around with that. So this is actually also a parameter that we went ahead and optimistically or with wishful thinking defined as a part of our constructor of the model. So I'm going to use the speed parameter of the model. And now that we have these two required parameters to be able to construct a cell object, let's go ahead and say, okay, self.population.append, and we're going to make a new cell with the starting location and the starting direction, right? Great. Now you may notice that we never used this variable I. And this is not uncommon when you're writing a loop that you just want to run some number of times. And a convention in Python is just to use the underscore to say, hey, I wanted to write a foreign loop, but I didn't need that variable that was being declared. So I'm just going to use sort of a single underscore to say, we just want this loop to run this number of times. We don't really care about that I variable. All right, so now we've got a population of cells. And the question is, will it show up? And how many cells will show up? We're not actually giving them random locations and directions yet, but that's okay because we'll come back to that. So if we look at where in the main module we're actually constructing our model, we'll see that we're constructing our model with whatever the constant cell count is. So if I look in constant cell count, we would see that currently we've got 1, and that's fine because they would all be at 0, 0 anyway. So okay, let's try running this project and seeing if it works. And what do you know? We've got a single solitary black circle here that is one of our cells. Now, if we wanted to, we could bump this up to say 10 for a cell count of 10. And when I run this again, notice all of our cells are on the same coordinate. So they are all on top of one another, and we haven't actually initialized to random directions. Before we go try and figure out where we should place our cells at random, let's look at the other constants we have available and talk about what they mean. So we've got some bounds or some boundaries in our simulation. We were saying the width of our simulation is going to be 400, the height is going to be 400. And because of the way Turtle Graphics works, where we center the origin of our window at 0, 0, that means we have negative values in the x-axis and negative values in the y-axis. That means that the minimum x value is going to be, the maximum x value would be the bounds width over 2. And the minimum x is going to be the negation of that, right? And so the intuition here, right, is if we've got our window and our width is 400, then if we're thinking about, well, where is the line that bisects this, right? Well, that's at 400 over 2. If we were to ask, okay, then that's where 0, 0 would be. So what would our max x be? Well, it would be that amount. It would be 200, right? And our min x would be negative 200. And so that's what we're computing here. You'll notice that something else we're doing is just building a little bit of a margin around the edge so that our dots won't ultimately disappear. So now that we know a little bit about these constants, what we want to do is make use of these constants in determining where do we randomly place our cells as we generate them. So we went ahead and with wishful thinking said, okay, we're going to make the starting location be whatever is returned from this random location method. So let's go ahead and try generating a random location. Well, we've got a function that we've imported from the random library that's named random. And this will give us back a float that is a value between 0 and 1.0, but not inclusive of 1.0. So what we can do is we can say, okay, let's say starting x is going to be random, and we can multiply that by constants dot, and we imported constants at the very top of this file, so now we can reference these. And I think what we want to multiply by here is the boundary width, right? So we have a total space, our domain is our width, and that's 400 pixels. And then what we want to do is we want to say, okay, well, we know that our x stops at 1/2 of that, right? So why don't we subtract the max x from it, or we could just add the min x. Either way, it's the same thing. All right, so let's subtract the max x, right? Which was oops, and we have to reference that from our constants import. Okay, and so now if we have our starting x, we can drop that in. So remember, this random location method is generating a new point, and we're saying, okay, rather than say 0, 0 each time, use start x. And we can try the same thing with start y. And random multiplied by constants dot bounds height minus constants dot max y, right? And yeah, this seems to be fine. And let's update this argument so that we use start y as well. All right, so now if this implementation works, when we start our program, we hope to see our dots or our cells randomly placed. So sure enough, they are, and we can try this again. Okay, cool. And we can try that again. Yep, it looks like each time we ran the simulation, when we initialized our model and we created these initial cells, they all started in random positions. Now they're not moving. And in order to make our cells move, we kind of need to do two different things. One, we'd really like them to move in random directions. But for now, let's just try making them move, +1 in the x direction and +1 in the y direction each time our model updates and each time we try and draw a new state to our program. So if we try this, and we're still stuck in one point in time. So why is that? Well, this is where we need to talk about the idea of a tick, right? So for right now, we're going to come back to this because we'd really like our cells to be moving in different directions, but we have no way of testing whether or not the implementation of this is quite correct. So the first thing we need to talk about is this idea of this tick method. And the view controller is going to be responsible for calling this method each time it tries to update the screen and move the model or the simulation to its next state. So here we're going ahead and incrementing our time attribute of our model by 1, just to say, okay, well, let's print out self.time and see and convince ourselves that this method is actually being called, even though our simulation currently looks like it's standing still, right? And notice down here, we've got 120, 160. So we're trying to run the simulation at a reasonable, what we call a frame rate. And it looks like we're updating, and tick is being called very frequently. And it's being called hopefully about 30 times a second. And for some reason, or I shouldn't say for some reason, but because we're not doing anything to change the state of our model in this method, nothing's actually changing, right? So what we'd really like to do is each tick of our model, which remember our model is going to have our list of every cell in its population. We'd like to say, okay, every cell, go update yourself based on your direction and your location. All right. So how can we do that? Well, if we want to say, okay, each time this method, this tick method is called, let's go call a method on every cell object that's in our population. We can say for each cell in our self.population, cell.tick, right? Tick isn't a method that exists on our cell class yet. Okay, so let's go implement a method named tick on our cell class. And just beneath part 1, I'd like you to try pausing the video here and seeing if you can declare this method. And we can actually go ahead and declare this together. So def tick is going to take it's going to need a parameter named self because it is a method, and it will return none. And what I'd like you to try doing is seeing if you can write, and it will only be one line of code, a line of code that will update the cell's location by adding the cell's current location to its direction, with its direction. And remember, there's an add method that's built into the point type. And so location and direction are both points. And pause the video here, see if you can get that working. All right, so hopefully you said something to the effect of the self.location is going to be reassigned self.location.add self.direction, right? This is a lot of dots, right? We haven't actually spent much time looking at what we call a chained invocation. And so here we're saying self, okay, that's the reference to the cell object, dot location, okay, that's going to be a reference to the point that is the location of the cell. Dot add is going to call the add method on that point, and we're going to give it a reference to our direction, just like we looked at in the previous video where we tried to trace through these steps in a memory diagram. Okay, so that's going to update our location to be at a new place. And we're doing this each time the simulation updates. And now what we're going to do is start our simulation. And sure enough, all of our cells, each time the screen updates, are moving up one and over one, up one and over one, right? And so that has the effect of when we start our simulation, it looks like they're all drifting out of our screen. All right. So we're now to the point of being able to actually generate a random direction. Remember, when we initialized all our cells, when we constructed our cells, we tried to give them a starting location and a starting direction. We randomized their location. Well, what about the direction? Well, let's try generating a random angle. So random angle in terms of radians will be pi, which was imported from the math.library. And I should say 2.0 pi, right? That's our radians multiplied by random. Right, so remember, randoms between 0 and 1, you think of it like a percentage, and this will give us that random angle. And then we can say, okay, dir x will be the cosine of random angle multiplied by, and this is where we're going to use that speed factor and kind of wave our hands and say this is sort of a magnitude multiplier, so multiplied by speed. And dir y will be the sine of that random angle. You thought you could avoid trigonometry, but it turns out it's really handy here. And then we will use those two values as our arguments. So dir x and dir y. All right. So now, if all is well, those are going pretty fast. But if we start our project and we see that it sure looks like they're going in different random directions from one another, and they're clearing the screen, right? So, okay, our cells are moving in random directions, but they're ignoring the bounds of our simulation. Now we've got this method here that was sort of, again, using wishful thinking, enumerated out. And now the question is, can we enforce the bounds? Can we say that when a cell goes just out of bounds, like say it goes just off one side of the screen in the X direction, so off of the side, can we, put it back so that it's not out of bounds, and then maybe flip its direction that it's headed in, right? So it's got a direction that says each time I update, this is the direction I'm going to be moving in, flips the direction such that it goes in the opposite direction along the x-axis. And same thing for top and bottom. Well, let's do one of these together, and then I'll turn it over to you to try and implement the remaining bounds or boundaries. Okay, so this method is going to need to move through, or it's given a single cell. So we should actually go ahead and set up, well, where do we actually call it? How does this method get called, right? This enforce bounds. Well, remember this tick method of our simulation is what's responsible for updating our state each time, right? Each time this method is being called, we're moving through each cell in our population. Cell.tick is what's updating the location of an individual cell. And now what we probably want to do is say cell self dot and enforce bounds is the method we're trying to call, and the cell, right? So we're saying, okay, I want to enforce the bounds, and the logic for that is going to be on the model. And you could imagine a world where that's defined in the cell as well, but we're going to define it in our model here. And now it's on us to say, okay, let's go just make sure that a cell hasn't gone out of bounds. And if it has, we'll apply some special logic. So how do we know if a cell has gone out of bounds? Well, remember, we've got these constants that tell us our max x and min x and so on. So we can say something like if, cell dot location dot x is greater than max x, say, then it's gone out of bounds along the right hand side of our x-axis. It's gone out that side of the window. So maybe we update cell.location.x to be max x. And not only do we want to bring it back in bounds, right? We could try this out. And you'll notice that I've got these red squigglies. That's because I forgot that we had imported our constants from the constants module, and we were prefixing all of our constants with the constants dot, right? So because we declared all those constants in constants.py, and at the top of our file, we said from projects PJ02 import this whole module named constants, then we can just say constants dot and then max x. All right. So with this logic, what we're going to see is cells are going to get stuck when they're moving in the direction of the right-hand side of our boundaries. They're going to get stuck along that right-hand side because we haven't updated their direction. But let's just see that this is the case, right? So we try this out, and sure enough, like this point here, boom, it got stuck, and now it's kind of just sliding along the y-axis, but stuck on that x, the far side of our screen, right? Okay, well, how do we flip the direction? Well, we can say cell dot direction, which was a point, dot x is going to be the same direction but flipped, right? So multiplied by -1, so it should move in the opposite direction. So we can try this out. And notice it happened only once and very quickly in that example, but you'll notice that as you try running this, when your cells hit their far x-axis, they change directions. They go in the opposite direction along the x. Now we're still not enforcing these boundaries along any of the other boundaries of our simulation. And we'll leave that exercise to you to be sure that no cells go outside of the y-axis or the min x off the left-hand side of the screen, the top or the bottom, right? And once you have that, we'll have a starting point for the next project. And in the next project, we'll be looking at adding some additional logic and constraints to our model, such that maybe we're worried about, as shown in the Washington Post example, what happens when two cells come into contact with one another and one's sick and the other one's not, and the contagion is passed on. And how can we model how long a cell has been sick for in order to make it become immune again? And we can start to add additional attributes and logic to our simple model that we've set up here of a 2D simulation in order to reproduce some of the work that you saw that was done in some great journalism out of the Washington Post, simulating transmission. And then we can play with some concepts that will be what will be open-ended about this project is giving you the idea to say, okay, what if I wanted to try modeling social distancing or part of the population wearing masks or something like that? Now, of course, this is a very, very simplistic model of the types of problems we face in the world, but we can still get a feel for the intuition behind some of the dynamics at play in our more complex real world systems by trying to model some of the same phenomenons in a simpler 2D environment. So this is the setup for the next project. And what we'll get started on as soon as that project is posted, we'll continue from this point to add additional modeling and simulation features to bring us closer and closer to what you saw in that Washington Post article. Great work.